Welcome back to my YouTube channel, and in today's video we are going to be treating a special case, which is the Laplace solving ODEs using Laplace transform. Solving ODEs using Laplace transform, which is a very efficient way of solving ODE, which is the ordinary differential equation. That is a scenario whereby you have the square y the x square plus the y the x plus 3 in scenario whereby we do not have a homogeneous equation, whereby we do not have an heterogeneous equation. That is this scenario. Now, one thing you need to know about ODEs is that they can be expressed in different form. This x cube x triple prime of t can be expressed as you have a big D here and then you have cube. It can also be expressed as the cube x the t cube. This can also be expressed as you put x. It can also be expressed as you put x, you put three dots on it. Depends on the version of the textbook in which you are using. So that is it for that. So now we need to move on to the question that we are solving here. Now that we have identified the different ways of expressing our ODEs. So now the question here says solve this using ODE. So how do we solve this? Now the Laplace transform of this. What is the Laplace transform of this? The Laplace transform of x triple prime of t, which is the same thing. Let me write it in its basic form. The cube x d t cube, which is its basic form. This here is equals to s cube times the Laplace transform of x. Now, in some books, you are going to see this as x bar. They are going to write this as x bar, which is the same thing as the Laplace transform of x. You just need to identify what we are talking about here. So now, x cube times the Laplace transform of x minus x squared times x naught. We have minus x times x prime naught minus x double prime naught. What you notice here is that we are having the value of s raised to power, the amount of time in which we are differentiating it, which is the order, the differentiation number, the order, yes, up to the point whereby we have s raised to power 0, and s raised to power 0 equals to 1 times the last differential of x naught. So that is it for the. You see, you notice a similar pattern here is that when we have the Laplace transform of the square x, the t square is going to be equals to s square. Then we have our Laplace transform of x, which is always going to be the first thing. Now, what is going to be different is going to be this. We have this our s, we have x of 0 before we have our minus. Since this is 1, then the next one is going to be this. Then we have x prime of 0. You can see the pattern that we have here. So we just need to understand how this pattern works, then you are going to be able to understand the Laplace transform of ODEs over there. So now, when we are going to solve this, the Laplace transform, we first start for the Laplace transform of s3 of t minus the Laplace transform of x double prime of t, and we have minus the Laplace equals to the Laplace transform of 0, right? This is what we are going to do. After finding for the Laplace transform, so this now is going to give us, to put this there, we have s cube times the Laplace transform of x, we have minus s squared times x, oh, let's just put it this way, times x naught minus s times x prime naught minus x double prime naught. Now, this here is for the Laplace transform of this alone. Then we move to this, we have minus. Now, the Laplace transform of this here is what we have as s squared the Laplace transform of x, we have minus s times x naught, and we have minus x prime naught. That this here is for the Laplace transform of this, and we have it as equals to Laplace transform of 0 is the same thing as 0. So now let us simplify this. Now what we need to know is that we have our boundary conditions inside the question, which is this, and they are always going to give you a boundary condition whenever they are asking you to solve an ODE question, unless it is something special. So moving on, our x naught, our x prime naught, and our x double prime naught is equal to 3. So this makes our job very easier. We have this as our s cube Laplace transform of x. Here we have minus s square. Our x naught is 3. X naught s square times 3, which can be expressed as 3s square. And here s double prime, we have minus 3s, we have minus 3. And in this other case, we have minus s square, the Laplace transform of x. We have s times x naught, we have minus 3s, we have minus 3 equals to 0. Now, due to this minus sign here, and we have minus 3s minus 3, we have minus 3s minus 3 cancels minus 3s minus 3. So that makes it simply more simple. Therefore, we are going to have this as the s square, s cube, Laplace transform of x. We have minus 3s square. Then here, if we open the bracket, we have minus s square Laplace transform of x here minus s square Laplace transform of x here is equal to 0. So one thing that we can do here is all the Laplace transform of x to one side, while the ones that do not have Laplace transform of x to the other side. So we have s cube Laplace transform of x minus s square Laplace transform of x. So this minus 3s goes to the other side, we have 3s as a whole. So we can just simplify this by bringing Laplace transform of x out and leaving out the constant. We have Laplace transform of x, and here we have s cube minus s square. S cube minus s square is equals to 3s. So what we do is divide both sides by s cube minus s square. So this cancels this. So therefore, here we are going to be having the Laplace transform of x is equals to 3s over s cube minus s square. S cube minus s square. So that is it for that. Therefore, we have and one s here can cancel one here to become square. Then here is going to be remaining one. This will be equals to 3 over s square minus s, which is equals to 3 over s into brackets s minus 1. So now from here we have our Laplace transform of x is equals to this. We find for the inverse Laplace transform of both sides. So therefore our Laplace transform of x is going to be equals to x, and then we find for the inverse Laplace transform of this in order to get our value for x. So the inverse Laplace transform of this, that is like the inverse Laplace transform of the Laplace transform of x, which is going to give us x. As the inverse Laplace transform cancels the Laplace transform, we are going to have our value x here is equal to the inverse Laplace transform of 3 over s into bracket s minus 1. 3 over s into brackets s minus 1. So now moving on, like if you have been following our series over here, we are going to know that in this scenario we are going to be using the division law of inverse Laplace transform. And in the division law of inverse Laplace transform is the integration from t to 0, from 0 to t of whatever you have as your f of s. So now this is going to be equal to the integration from 0 to t of 3 over s minus 1 is going to give us 3 e where 1 over x minus k is going to give us a over 8. 3e raised power k is 1t plus 3e raised power t. And the integration of this is going to give us, is still going to be e raised power t. So we are going to be having 3 e raised power t minus 3 as our final answer. So in this scenario, if you are confused about this, you can check out my initial videos on inverse Laplace transform, so you can be able to get this. So now, as you've seen here, we can agree that the way of solving ODEs using Laplace transform is that you find for the Laplace transform, then after you finish your simultaneously solving it, you getting the solution of the formula as Laplace transform of x, you find for the inverse Laplace transform so that you can get the value of x, and that is how you solve it. Thank you very much. My name is Ejina Incredible. Don't forget to subscribe, like, comment, and share.